Okay, lesson 10.2, using the fundamental counting principle. And so our objectives are to know the meaning of uniformity in understanding the fundamental counting principle, use the fundamental counting principle to solve counting problems, and use factorials to determine the number of arrangements. Uniformity. Basically, we talk about uniformity like in you say that wearing masks on campus, everybody's uniformly wearing masks or screen. So basically, everything's the same. Like if you're talking about the military, everybody wears a uniform, so they're uniformly wearing the same thing. So when we talk about uniformity, numbers, no matter which choice is selected, the results are the same. Okay, in the fundamental counting principle, we have different tasks. And for each task, we have one and two and three and so on. So we can look at, for example, a license plate. In the license plate, you have 3 letters and 4 numbers in North Carolina. Well, each letter the first letter would be on 1, the second letter would be on 2, third letter would be on 3, and then the next would be the first number and 4 and 5 and 6 and then 7 for the 4 numbers. So in each one of these, we look at total number of possibilities for each one. So for the fundamental counting principle, we're going to multiply the number of possibilities for the first letter, number of possibilities for the second, and so on. And then the product of all that is going to be the total number of possibilities that we can have as a result. So for example, if we're looking at the number 0, 1, 2, 3, 4, 5, okay, let's look at that on our board. Okay, so if we're looking at the numbers in the set 0, 1, 2, 3, 4, 5, and we want to know how many 2-digit numbers we can come up with. Well, here's the first digit and the second digit. But the first digit is not having 0. So we would say, all right, well, we could have 1, 2, 3, 4, 5. So that would be a total of 5. N1 would be 5. So now for N2, all right, we can have a 0, and we can have 1, 2, 3, 4, 5. So how many possibilities can we have in the second digit? Well, this one's 1 more than the first one, right? So this would be what? 6. So what we do here is, so N1 is the first digit, N2 is the second digit. So basically what we're saying here is if we multiply these two arrangements, these two possibilities, N1 times N2, we would get a total number of ways we could arrange 2-digit numbers using the set 0, 1, 2, 3, 4, 5. And so 6 times 5 is what? Yeah, 30. So there's 30 different ways, 30 different numbers that we can arrange the digits 0, 1, 2, 3, 4, 5, where 0 is not counted as the first digit. because we don't normally write 0, 2, right? We just write 2 or 3. But we can have 0 at the end, like 20, right? So that's why we set the restriction where 0 cannot be the first number. Okay? Any questions with that? So they use a table here. I like to list all the possibilities because it's right there in front. You can't mistake what we have here. All right. Any questions with that? All right. So what we're talking about here is we can have like 1, 2, 3, 4, 5. But not 6, because 6 is not in the set. So we can have 1, 2, 3, 4, 5, and then 10, 20, 30, 40, 50, and then 11, 12, 13, 14, 15. As long as it's in the set 0 through 1, 0, 1, 2, 3, 4, 5, then we would come up with 30 different ways. Okay, how many digits can be made where the numbers, how many 2-digit numbers that do not contain repeat digits? So basically with this one, we said before that we cannot start with a 0, right? So it's still 1, 2, 3, 4, 5. Now, if we selected one of the numbers, right? Like, for example, if the number is 20 something. And okay, so if we selected a 2, right? If we selected a 2, then 2 cannot be in the second digit because now the restriction is the digits can't be repeated. So it can be a 20, a 21, a 23, 24, 25, but it can't be a 22 because we're setting the restriction that digits cannot repeat. So now we have how many digits do we have for this? How many numbers do we have for the second digit? If we cannot repeat, it's not 6 anymore. Now it's what? If we can't repeat one of them, it's not 6. That means it would have to be what? 5, right? So therefore, 5 times 5 would be what? 25. So that would mean that it cannot repeat. Then we can only have 25 different ways to arrange 2-digit numbers in the set 0, 1, 2, 3, 4, 5. Okay. All right. Any questions with that? All right. Okay. How many ways can you select 2 letters followed by 3 digits for an ID card? Okay. So you got 2. So you got 2 letters, right? So we've got letter, and then we have, I believe it was 4 digits. Right? Yeah, 4. That was 4 digits. No, 3 digits. First letter, second letter, 3 digits. Okay, so we've got letter, and then digit, and digit. Okay. So we've got the first letter. Now there's no restrictions. So we're talking about A, B, C, all the way through the alphabet, X, Y, Z. So how many letters are there in the alphabet? There's 26, right? And so for the second letter, again, A, B, C, all the way through to X, Y, Z. Again, there's 26. Okay, so we've got, this would be N1, right, times N2. So we've got 26 times 26. Now we're looking at digits, right? So when we're talking about digits, we're talking about 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 5, 6, 7, 8, 9. Single digits. And restriction this time. You can select 2 letters followed by 3 digits. So since this ID starts with letters and not numbers, you can have the first digit as a 0. And so how many digits do we have? We've got 1 through 9 plus 0 is 10, right? So that's 26 times 26 times 10. And then again, 0, 1, 2, all the way to 8, 9, 10. That's 10. So that's first digit, second digit, third digit. Again, 0 through 9, or there's just 9, not 10. So that's 10. So right here, 10 times 10 times 10, well, 10 times 10 is 100. 100 times 10 is 1,000, right? So we're talking about 26 times 26 times 1,000. So if you go on your calculator, okay, and you put in here 26 times 26, and you could do times 10 times 10 times 10, or you could put in 1,000 times 1,000, one more. You get 676,000. So 676,000. So this is N1 and times N2 times N3 times N4 times N5. So when we were talking about the uniformity, right, back here, uniformity of criterion, we're talking about each one of these is uniformity. You're going to have the same number of letters in the first one and the second one, same number of digits in the first one, second, third. So it's uniform. They're equal in the possibility of selecting it. And here's our fundamental counting principle, and 1, 2, and 3, and so on. And that's what we have here. Okay, so that's what we're talking about, the fundamental counting principle. So what we're saying here is that given that if we were to, how many possible ways can we come up with ID numbers? We can get 676,000 different ways to come up with an ID number based on 2 letters followed by 3 digits. Okay? So any questions with that? And that's part of the fundamental counting principle. All right? Okay, so this can be useful information, like if Livingstone College anticipates having, 10,000 students in 5 years, then, they may want to go with 2 digits followed by 2 numbers, or they can use 4 digits and so on. All right. Any questions with that? Okay, factorial. Factorial is a number of ways of we're counting numbers down through 1. So in other words, if we have 5 factorial, then your 5 factorial would be 5 times 4 times 3 times 2 times 1. Well, why would we want to do it that way? Well, if let's say we have 5 students, and we have 5 ways to arrange the seating in the first row. 1, 2, 3, 4, 5. And we have 5 students. So 5 students any one of 5 students could be in the first seat. Well, if one student, so if you took the first seat, right, now there's only 4. So the next student takes that one. Now the next seat, there's only 3. And the next one, 2 and 1. So that's how factorial can be useful in coming up with ways to arrange things, or in this case, order matters. Okay, so factorial, and that's where we get into n times n minus 1 times n minus 2 and so on. So if we're talking about 4 factorial, for example, right? Okay, so on 4 factorial, that would be the same thing as if we said 4 times 3 times 2 times 1. So 3 times 4 is what? So now we multiply, right? 3 times 4 is 12. 12 times 2 is 24. 24 times 1 is 24. So 4 factorial is 24. Okay, can we go ahead and get off the cell phones, please? Appreciate it. So our answer here for 4 factorial is 24. Now on the calculator, all right, you can go here to where it says, on this one here, if you got a scientific calculator, you can go, in this particular one, you can go to PRB, and then you see here it's got, well, the glare kind of, there, that's a little better. You can see where the factorial button is. So basically, if we put in 4, right, and then go to PRB, and then right arrow over to the factorial sign, there you go. It's like an exclamation point, and then you hit equals, you get the answer. So you can use your calculator to work with factorials. All right, any questions with that? So the next one, 4 minus 1, and then 5 over 3. Okay, so the next one, you've got 4 minus 1, parentheses, factorial. Basically, order of operations is to simplify inside the parentheses, right? So 4 minus 3, that's what? 4 minus 1, that's 3 factorial, right? And so 3 factorial is going to be what multiplied out? 3 times what? 2 times 1. So 3 factorial is actually, what's 3 times 2? 6 times 1 is 6. So 3 factorial is 6. Okay? All right, questions there. So if we had 4 seats, right, and 4 students, the first seat could have 4 students in it, second seat. So if 1 student sat down, then the next seat would only have 3. Next seat 2, next seat 1. So with 4 seats and 4 students, there's 24 different ways to arrange the seating. Okay, so that's how that can be useful. All right, any questions with that? All right, next we have 5 factorial or 3 factorial. That's what it was. Yeah. All right, 5 factorial over 3 factorial. Now here, you can multiply this out. 5, excuse me, times 4, times 3, times 2, times 1, over 3 factorial will be 3 times 2 times 1. Well, the 3's can cancel, right? 3's cancel, they go to 1. 2's cancel, they go to 1. And the 1's cancel. So really what you have here is 5 times 4. After you simplify it out, which is what? What's 5 times 4? 20, right? Well, you could do this another way too, where you have 5 factorial over 3 factorial, and you could just go as far as the 3 factorial. So in other words, 5 times 4 times 3 factorial over 3 factorial, and then just cancel out the 3 factorials, because you get the same thing here, and so you still get 5 times 4, which is 20. Okay, so that's just an easier way to simplify things out. So for example, if you had 99 factorial over 98 factorial, instead of writing out 99, 98, 97, 96, 95, all the way down, you could say, all right, 99 times 98 factorial over 98 factorial, cancel the 98 factorials out, and you just get 99. Okay? Questions there? Okay. Zero factorial is 1. Okay? Why is that? Because when we get into permutations and combinations, you'll see why. But for right now, just note that 0 factorial is 1. And so I believe if you even do that on the calculator, 0 factorial, you should get 1. Let's see if we do. 0, here be, yeah, you get 1 on the calculator as well. Okay. All right. Arrangements of objects. When finding the total number of ways to arrange a given number of distinct objects, we can use factorial. And that's what I was talking about, arranging the seating. 5 students with 5 seats and so on, where you can only have one person. One person can only sit in one seat at a time. Okay, so we can use factorial in that case. The total number of different ways of arranging n distinct objects is n factorial. Okay, different ways of, so we use factorial when we're looking at different ways of arranging things. How many ways can a lineup of 6 different books? So we're talking about books this time instead of seating arrangements, right? So we're talking about 6 factorial, right? We're talking about different ways of arranging a book. So we're talking about 6 times 5 times 4 times 3 times 2 times 1. So 6 times 5 is 30, right? 30 times 4, if 3 times 4 is 12, then 30 times 4 is 120. And 120 times 3 is 360, 720. Okay? So the 6 factorial is the same thing as 720. All right? Questions there. So what does that tell you as far as books go? How many different ways can we arrange the books on a shelf with 6 books? Yeah, 720 different ways, right? Okay. Arrangements of n objects containing lookalikes. In other words, if we want the number of distinguishable arrangements of objects where there's a repeat, so where you have more than one of that same kind, then you use n factorial over the total factorial over the number of different items that have repeaters in them. So let's see how that works. So if we're looking at the number of ways of arranging initially, okay, INITIALLY, okay, so Let's look at that. So we want the number of ways of arranging the letters initially. Okay. You got 1, 2, 3, 4, 5, 6, 7, 8, 9. So the total is 9. But we have some, so that's our n factorial. But we have some repeaters, right? I, how many i's do we have? Upper or lowercase? Yeah, we have 3. And what else repeats? The l's, right? And how many of those do we have? 2. So this would be the n1 and this would be n2. So we're talking about n factorial over n1 factorial n2 factorial. So you take the total, which is 9 factorial, over the number of i's that repeat, 3 factorial, over the number of l's that repeat, times 2 factorial. Okay, so basically we're going to go 9 times 8 times 7, and we're going to go out to times 7 times 6. How far out are we going to go? Times 5 times 4 times 3 factorial, right? Because the 3 factorials can cancel. And then the 2, we can multiply 2 times 1 out. So the 3 factorials can cancel, right? And 2, that can cancel into any of the even numbers. 2 can cancel into 4, 6, or 8. I like to cancel that out with the largest. And 1, that's just 1. So basically what we have here is 9 times 4 times 7 times 6 times 5 times 4. Okay, questions with that? So if we multiply this out on the calculator, 9 times 4 times 7 times 6 times 5 times 4, and hit equal, we get 30,240. So what that's saying is we can arrange, we get 30,240 ways of arranging the letters in initially, since we have 2 L's and 3 I's. It's not going to be 9 factorial because you can't, I mean, the I's, you have 3 I's that are always going to be the same. So you have to take that into the repeating letters into consideration. Okay? Questions with that? Okay. Any questions at all with lesson 10.2? Let's see if there's anything unusual. All right. All right, let's look at one of the homework problems real quick. So on the homework, problem 9, you've got baseball manager has 11 players of the same ability. How many 9-player starting lineups can he create? So you would have you would have player, you have position 1, position 2, position 3, position 4, position 5, 6, 7, 8, and 9, right? And how many players, given that each player has equal likelihood of playing, how many players can be in the first position? Well, how many players does he have? 11, right? So he's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So he's got 11 players. That would